Go for it. Thank you.
Hello, everybody. Welcome to my talk on aerosol and cloud observations with ground-based remote sensing instruments at Punta Arenas, Chile. I will focus on heterogeneous ice formation in shallow stratiform clouds and compare the results we obtained from the observations in the Southern Hemisphere mid-latitudes to the Northern Hemisphere. My name is Martin Radenz, and I finished my PhD at TROPOS Leipzig earlier this year. This talk is only to provide an overview. More details can be found in the ACP paper we published end of last year. I will focus on stratiform clouds in the southern mid-latitudes, as they still pose challenges to climate models. Especially the high abundance of supercooled liquid layers is not well covered in the models and biases the radiation budget. A better characterization of these stratiform clouds is needed, especially how frequently they form ice. Our study is based on observations obtained with the mobile instrument suite LACROS. This is an acronym for Leipzig Aerosol and Cloud Remote Observation System. The focus is on observation of aerosol-cloud interaction at key locations of the climate system. Here you can see a picture of the site at the campus of the University of Magallanes at Punta Arenas. LACROS consists of a collection of instruments. Most important are a multi-wavelength Raman polarization lidar poly-XT, aka band cloud radar, and a Doppler lidar. For the campaign at Punta Arenas, also additional instruments are co-located by partner institutions. I want to highlight some more observations we did here, which are the hilltop in situ aerosol sampling we did at an upwind location. Over the last decade, LACROS was deployed to 3 multi-year campaigns at Leipzig, Central Europe, Limassol in the Eastern Mediterranean Sea, and recently to Punta Arenas in the southernmost extremities of South America. Overall data coverage is quite comprehensive. Limassol covers 1.5 years of synergistic radar-lidar observations in the Eastern Mediterranean and is the first such dataset in that region. At Punta Arenas, we cover now 3 years, and it's the only ground-based dataset available from the western half of the Southern Ocean and one of the longest records south of 45 degrees south. In terms of aerosol, the locations are quite different. Leipzig is a typical continental northern hemispheric site, whereas Limassol is influenced by a multitude of different aerosol sources, such as the Saharan and Arabian dust, marine and continental aerosols. Punta Arenas, on the other hand, at least in the free troposphere, is only subject to pristine air masses from the Southern Ocean. The figure on the left shows profiles of aerosol extinction coefficient based on the LACROS lidar observations with temperature as a vertical coordinate. For all locations, we can see 2 regimes and a strong degrees of extinction at heights with temperatures between 0 and -10 degrees Celsius. Colder temperatures are associated with the pre-troposphere and warmer temperatures with the boundary layer. Generally, the lowest extinction coefficients of the 3 sites are found at Punta Arenas. To derive statistics on the frequency of ice formation in stratiform clouds, we rely on the synergistic cloudnet retrieval, especially the target classifications. Shown is a measurement example from November 2018, when we began our measurements. A time height plot of cloud radar reflectivity is shown atop, the lidar backscatter on the bottom left of this slide. The derived target categorization is shown in the middle. During the shown period, 3 stratiform clouds with supercooled liquid tops were observed. The 3 clouds show the typical structure of such a stratiform mixed-phase cloud, with liquid droplets at cloud top, and if ice is produced, a virga below. For the analysis, an automated cloud identification scheme is used. The clouds detected during this particular period are marked with rectangles. Overall, in our dataset, there are more than 2,500 clouds that were detected, and now we divide them into ice-forming and liquid-only clouds and bin them by cloud top temperature. From there, we can calculate the fraction of clouds containing ice at each cloud top temperature. But the curves we got there do not look like we expected. Even for very low temperatures at Punta Arenas, 40% of the clouds were identified as liquid only, which cannot be explained by aerosol-related differences alone. Also, for slightly supercooling temperatures, only very weak contrasts were found. But with the comprehensive instrumentation at hand, we can have a more detailed look into these clouds. First, we need to consider wave clouds. Shown is another observation example with the target categorization on top and the Doppler lidar vertical velocity at the bottom. This time, a typical wave cloud is observed, where liquid and ice phases are separated horizontally. Such a structure is well known in the literature, but this situation is hard to identify for a location-fixed observer, especially if the ice tail is not affected over the side. In this case, the cloud is classified as liquid only at a cloud top temperature below -30 degrees Celsius. However, the Doppler lidar vertical motion observations can help us here. The slow changes in vertical velocity indicate a laminar wave-induced flow and have a long autocorrelation time. The autocorrelation function can be analyzed for all the clouds in all the three datasets. Shown here now is just an overview over the liquid clouds at Punta Arenas, colored by cloud top temperature, and we can already see that the colder the liquid-only clouds, the longer the autocorrelation tends to be. To get an better overview, now the autocorrelation functions are clustered into intervals of 5 degrees Celsius of cloud top temperature. The line shows the mean for each cluster plus the 10 to 90% percentile for the warmest and coldest cluster, which are -5 degrees Celsius and -35 degrees Celsius. Now we can start to filter our wave clouds from the dataset. For each cloud, we get the length where the autocorrelation function drops below a value of 0.8, and then step by step exclude these clouds from the dataset from autocorrelation length of 30 kilometers down to 300 meters. If we do so, we gradually increase the fraction of ice-containing clouds and get to very high fraction of ice-containing clouds for temperatures below around -40 degrees Celsius. However, these wave clouds could not explain the very weak differences at slightly supercooling temperatures. For the slightly supercooled clouds, we have to go back to the lidar-derived optical properties. By combining the lidar observations with air mass source estimates and well-known INP parametrizations, an estimate of average INP concentrations for different ambient temperatures can be obtained. Shading in these plots highlight the variability due to different air mass composition. Here we can discriminate three regimes: the free troposphere for cold temperatures and the boundary layer for warm temperatures with a transition zone in between, which also fits the optical extinction profiles we saw earlier. Based on this information, we can separate the dataset into clouds that are coupled to the boundary layer and those that are uncoupled, giving us a refined statistics. Here we can see that for slightly supercooled temperatures, coupling to the surface increases the frequency of ice formation. Finally, after considering both aspects, so the boundary layer coupling and the wave effect, the fraction of ice-containing clouds for free tropospheric and non-wave conditions can be estimated. The remaining difference in ice formation frequency between the three sides can then be attributed to differences in the aerosol properties. At Punta Arenas, ice formation is less frequent at temperatures where ice nucleating particles are at least a factor of 10 less common. Additionally, we could show that the ice virga at Punta Arenas contained less ice mass and had a lower ice-to-liquid content ratio. Now I want to sum up some key messages. We confirmed hemispheric contrast in ice formation of shallow supercooled clouds that are likely linked to a lower aerosol load. but those differences are less pronounced than suggested by previous studies. Second, a higher frequency of ice-containing clouds in the radar-lidar dataset was found compared to the well-known lidar-only datasets that are also referenced here. This is due to an increased sensitivity of the cloud radar to low ice water contents. Third, surface coupling of the cloud increases the frequency of ice formation, which is also the case for Arctic clouds, which was shown by my colleague Hannes Grieche in a paper also last year. And finally, vertical velocity observations are urgently needed to understand liquid layers at cold cloud top temperatures. Now I want to advertise an upcoming campaign. We will bring a similar set of remote sensing instruments to Neumayer 3 station, Antarctica, end of this year. And we will plan to cover the full year of 2023 with observations that produce basically a similar data set as was used for this study. The focus here will be on cloud properties, especially when transport of aerosol and moisture from lower latitudes towards the continent occurs. With that, I want to thank you for your attention, and I'm happy to answer any questions.
Thanks. And Martin is online, so are there any questions? Yes.
Yeah. Thank you for this really interesting study. Actually, you partially answered my question with your last slide that you will continue these measurements in Neumayer. But my question was, so you said that, yeah, your measurements in Punta Arenas are actually representative of the upstream conditions over the Southern Ocean. And I was wondering, well, if you already have any hints, is it really representative also of the downstream conditions, or it picks up some really lots of local continental sources of aerosols that will be actually changing the composition and the amount and the type of the aerosols in the downstream when it goes towards Antarctica?
That's actually a good question. So we are, there's a follow-up study on the in situ measurements I briefly mentioned that was recently published in ACP, but we do not know what the effects are. So we only know that the terrestrial landmass there is a rather prominent IMP source, but we have no idea how that plays out in the downstream area of South America. So this is still a question to be answered. But currently, apart from Neumayer, I do not have any activities planned in that area.
Do you plan to, sorry if I can have a follow-up question, do you plan or do you know of any similar measurements on the peninsula? Because there would be really rare case that you would have the Pacific flow crossing over the southern South America or into Atlantic and then get into Neumayer. So that's, yeah. So you would have more often that it actually continues towards the peninsula or, yeah, like even Western Peninsula. So do you have any knowledge of the measurements there?
As far as I know, there are not a lot of measurements available there, so nothing comparable to the stuff I presented, but maybe there's some more knowledge in the audience on that.
Well, there are the event studies, but yeah, we can maybe discuss this later. But okay, thank you.
Thanks. We have time for one more question. Okay, thanks.
All right, thank you, Martin, for joining.
Thanks.